Okay, guys, this is the continuation of the problem that we were solving. We did the previous video, the part corresponding to C. Now I'm gonna do the part corresponding to D, the internal forces at the point D. And this is important, okay? The last part we explained and we did this problem, and then we say, oh, calculate the reactions is the first thing. So we came and we calculated the reactions and we put all the values. Where are my reactions here? Reaction forces, we put all the values for the reaction with the summation of moment, we calculated, and then at the end we realized that there is not the need for doing this because the beam was symmetric, the loads and the geometry, and then we could just know that this is 40 because the total vertical load coming down was 80. But anyway, you reviewed this part of the problem when we calculated those values, and now let's continue. This part is asking for internal forces at the point D, and the point D is here. Now this is what most of the people do. You have to make a cut there, right? So if you make a cut there, I'm gonna tell you what is the main error that most of the students do. I make the cut here, right here, you see? Point D, right there, slanted. It's not supposed to be slanted. Now, this value for By is 40, this value for... As a matter of fact, the students don't even do that. Most of the students do this. Let me show you exactly what they do. They get this problem like that. I'm gonna bend this so you don't... This part is not seeable. Okay, there you go. So this is live, guys. I don't have editing, so everything that I'm producing is real time. So what we're doing here, most of the students, is this. I'm gonna make a cut right there because it's the other point where the problem is asking us to do. So the students do this. Okay, this is my beam. I'm gonna cut it here. So if I'm gonna cut it here, I'm gonna take this side of the beam. I have this moment like that. This force coming from this is zero force here, which is 15 coming from the triangle. This other force here coming from here, which is 40. The force coming from the total rectangle goes at the center, and that's a 50 kip. And then I have the reaction here from the support B, which is another 40, and this is the point that I have to do it. If you realize this load, the load coming from this triangle, falls into this distance here is 1 meter, which is what we have to do. This force is falling 2 meters. So that force should be in this side of the beam, and I have to do the cut here. And then they say, okay, that force coming from this triangle, the resultant is acting not within my cut. So if I'm studying this side, that force should be out and I shouldn't be taken into account, and then I do this for my shear and this for my moment. And if I select the other side, which is this part, then in the other side, which is this, I put the total force here of 15 kips, and then I put my shear and my moment. Well, guess what? This is wrong. And even some books tells you to do that. Some books tell you, oh, this is an approximate method. Approximate? No, it's not approximate. What you have to do, and I really want you to do it like this. I mean, don't shred my exam or my problems while you're doing it, and definitely don't cut yourself. But what you're gonna do, or what I want you to do, is this. Let me get my, you see, nice katana. This is not Michon's, by the way. What you're gonna do is that if this is the point D, and I have to cut it right there where the point D is, point D, look what happened when you cut it there. If you cut it, definitely this is what is happening. You cut it there, and then when you do the cut, this is what happens. You separate the structure in two parts, and whatever is on top of the cut is still on top of the cut. Remember, this 15 force, that's a lie. That's something that we do only for calculating reactions, external reactions. But when I do the cut, this part of the beam carries a part of the triangular load as well as this other part of the beam, and that's what we have to do. So if we are going to study, obviously I'm not going to study this side because it's longer, so I'm going to study this side. But if I'm going to study this side here, I cut myself, look, with the katana. No, just kidding. This is just coffee mixed with the ink. If I'm going to study this side, remember the V is going to be like that, and the moment at D is going to be like that. And if I'm studying this side, then the V is going to be like that, and the moment is going to be like that. And I select whatever side. Of course, this side is easier to see. So if you're using this side here for solving the problem, you say, I have to calculate this height. How much is that height? Well, you have a triangle there that is acting like that. This triangle, the total triangle, this is 5, and the distance from here to here, total distance 5, and the total distance is 6. Right now I made a cut, and this distance is 1, meaning this other distance is 5. I need to find this height. How do you find that height? You do a triangle relation. This is the height that I'm looking for. I'm gonna call it y, and you say, well, 5 is up to 6. 5 is up to 6, as y is up to 5. Or you can say the tangent of this angle is the same. What is the tangent of this angle? 5 divided by 6. But the tangent of this angle is also y divided by 5. That's why you have it like that. So then y is going to be equal to 25 times 6. And 25 times 6 divided by 6, I'm sorry. 25 divided by 6 is 4.16. 4.16 periodic here. And that's going to be the height of this triangle. Now you go back here and you say, okay, this height is 4.16 periodic kip per foot. Once you have that, basically your problem is solved, because you come here and you say, okay, let's do this part then, and let's say summation of forces in y equals 0. So you say VD minus what? Minus the force coming from this triangle. What is the force coming from that triangle? Well, it's 4. Remember, the distance from here to here is 5. That's the distance that we have to calculate it, because our cut for the point D is 1 meter from here. Remember, in the original problem it says that. I just cut it there. 4.16 periodic, that's the height, multiplied by the base, which is 5, divided by 2. That's the area. That's the equivalent force coming from this small triangle, and I don't have anything else. Equals 0, so VD could be equal, or would be equal to distance 5 divided by 2, 41. What was the value? 4.16 times 5 divided by 2 is 10.416 kip. And if I want to calculate the moment, then I do the same thing. I said the moment is going to be equal to a summation of moments at D equals 0. Then I have negative MD, because it's acting like that. This MD here. Now the force coming from here is this value, the area, 10.416 periodic, and it's acting in this direction, also negative, multiplied by the distance. The distance from here to here is 1/3 of the base, and the base is 5, so 1/3 of 5, and I have this other moment here, minus 15 equals 0. So my moment at D is going to be, if I pass this to the other side, it's going to be negative, and this is this value multiplied by 5 divided by 3 minus 15, no, plus 15, because that value, yeah, that's going to be equal to 32.36 kip feet, and that will be the moment. So the key point in this problem is, whenever you do the cut, you have to bring everything that the beam has on top of that. Now I'm gonna encourage you to do this side just to compare the results and see if these results are correct. I hope these are correct, guys. I didn't check these results before, so I really hope they are correct. You can also check them and let me know. Let me know if I made an error, which it might happen. I don't know. I don't think I did, but keep watching, guys. Good luck in the exam, by the way.